Welcome to the Math Primary Python Bootcamp session for supplementary. My name is Calvin. I have a math bachelor's. I have a computer science PhD, so I hope I know what I'm talking about when it comes to math. The goal of today is to give you a very light introduction to how math is used in learning. This is intended to be accessible in the sense that I'm not going to teach you how to calculate derivatives or any of that type of stuff. I'm going to tell you just mostly about the intuition behind some of these techniques that we use in mathematics. All right. So if you guys were in core or in the interest meeting, you may have heard that the minimum knowledge you need is calculus and linear algebra. So that's what we're going to go over today. Oh, by the way, the slides are also, so it's recorded and the slides are online. So it's better if you want to take notes, it's okay, but I don't think you need to take notes. So the order we're going to do it, we're going to talk about calculus, then linear algebra, and then just talk about a couple of other mathematical branches where you can use math in machine learning. Now, why this order, right? So notice what I put there, right? I put the, let me just see my time here, just so I know how fast to pace myself. Okay, notice I say calculus is the engine of machine learning, but then I say linear algebra is the building blocks and the gears of machine learning. And why did I put linear algebra at the second one there? I only do it mostly because I'm assuming most of you guys know calculus already, and not many of you know about linear algebra. So I thought just go through the easy stuff first, so stuff that you guys know already, and then we go on to stuff that you're not familiar with. So that's why I did it in this order. It should be really the other way around. All right, so let's start with calculus stuff. I borrowed a lot of the content here from a nice text, a book called Deep Learning for Python, written by Francois Joly. I don't know how to pronounce his name. He's actually the creator of Keras, and he works for Google now. So he quotes it as the engine of deep learning, and I do agree with that. Let me tell you why. So, what is machine learning? This is a very widely quoted quote. I'll read it to you. A computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task in T as measured by P improves with experience E. Okay, that's it. So this is one definition of machine learning, and it's very highly quoted. And the thing that I like to take from this quote is that the way how machines learn is by trying to optimize some function. So try to optimize a performance measure. So they learn, you give it data, you give it labels, and it tries its best to predict the labels as best as it can as measured by a quote loss function. So the main thing I want to take out from here is that machine learning algorithms usually try to minimize the loss function. So now you hear that word minimize, and that's where calculus comes in. So the point is that you want to optimize something. You want to find the lowest value of a function. In nonlinear functions, you generally want to you have to find a way to minimize the loss function. So we're going to use calculus to do that. Okay. So before we get into the main thing that drives all these algorithms, which is going to be gradients and derivatives and stuff, I want to motivate them beforehand. Now I saw that some people are already taking calculus 1. So everyone is taking calculus 1. That's right? So everyone is taking calculus 1?
Yes.
Okay, so I'm going to breeze through this really quickly since you guys already know about derivatives then. So we know how to calculate the slope of a straight line. You simply, if you know the form already, so y equals mx plus b, it's simply just m. Or let's say you just had a line. You can simply take 2 points, use that formula, and then you get the slope. But this doesn't really seem to make sense for if it's not linear. It doesn't seem to be defined. But one way you can do it is just simply take 2 points on a curve and then measure the slope, and you can treat that as sort of it's like a rate of change between these 2 points, but it's more of like an approximation. So if you connect the two points, these 2 points here with a straight line, we call that a secant line, and then the slope of the secant line is the rate of change between these 2 points. And it's more of in some sense, approximation of how fast does this curve change. So you guys already know about this. What if c and x are very close? So what if this point is very close to that? And you keep measuring the slope. The slope is going to converge to some value, right? So they're going to converge to some value. And what if it's very, very close that it just simply touches the curve? We call this the tangent line. If a line is sloped such that it only touches one point, we call that a tangent line. And we define the slope at this point to be the slope of the tangent line. And usually we call this the instantaneous rate of change. Am I pacing fairly well?
Yeah, pretty good.
Okay. All right, so now you're starting to get where we're going at. It's time to talk about derivatives, right? The derivative, so I'll just read through the slides. The derivative of a function at a point is the instantaneous rate of change at that point. The derivative at the point is the slope of the tangent line at that point. And they're a very fundamental tool of calculus. So one example is the derivative of the position of a moving object with respect to time is the object's velocity. This measures how quickly the position of the object changes to time. So the main thing to take away from here is just that it is the instantaneous rate of change at that point. Okay, so why is this important, right? Talk about one theorem that you guys already know. I'm going to just state it. Now, it looks like a lot of people know a fair amount of math. I don't think anyone is very fancy with your math, but I just included just this theorem just to satisfy some of the math majors. So let me read it just off the slides, and then I'll explain why did I even put this on the slide. Okay, so let I be an open interval containing the point x0, and suppose that the function f from I to r is a set of real numbers, I couldn't find the font for it, has a second derivative. Suppose that the derivative at x0 is equal to 0. If the second derivative at that point is greater than 0, then x0 is a local minimizer of f. If the second derivative at x0 is less than 0, then x0 is a local maximizer of f. You don't need to worry what this means, but I know you guys already took Calc 1, so you guys know what this is saying. What this is saying is that how do we minimize a function? How do we find where is a minimum, if something is a minimum or maximum? What we do is that we take the derivative of the function and we set the derivative equal to 0. We call those critical points, right?
Critical points, yeah.
So you find the critical points. So these are like areas of interest. Then you use the second derivative to determine whether it's a local minima or maxima. So the thing is that it's 0, you can't just simply say, oh, it's a minimum or maximum. You can't just simply say that. You need to do another check, which is using the second derivative. So I know this is recorded, so don't worry if you don't know what a second derivative is. That's not really important right now. And then, once you have found out which of the critical points are, say, minimums, let's say you're trying to find a minimum, you can just simply evaluate all those minimums, find what the output is of the function, and just choose the one that has the lowest value. And that is your global minimum. So yeah, you choose the point which yields the smallest value. But of course, this is probably not the best thing to do for complex functions. When I say complex, I mean things like really hard to derive, like if you have sine times cosine over e to the x or something. I don't mean like complex valued functions. So it's
something that's like really oscillating. Like
yeah,
really bad.
Like if you have to use like say product rule, quotient rule, you do not want to do that on a test, right? Yeah. So this method here. So the point is that in machine learning, some of the loss functions you'll encounter are actually really they're compositions of functions, and these compositions can go like hundreds of layers, and it is really difficult to simply just find the derivative of that function. So that's what I'm trying to say when I say this procedure is infeasible for complex functions. Okay, so the point of that last slide is to show you why we study derivatives. Derivatives are useful because you can use these derivatives to find where the minima is. But that example, the theorem was only talking about just one dimension. So if your independent variable is x and you want to have an output y. So we want to do a multiple dimensions this time. So we'll take a simple example. Now we're going to 2D. This is where it gets to Calc 3 material. I'm going to try my best to explain it. I want to talk about a special object called a gradient, but before that, just for the sake of completeness, I want to introduce partial derivatives. So what is a partial derivative? So you guys may have noticed. So I am going to skip a little bit. So I think everyone's taking Calc 1. So that means you guys know about integration then. You notice that professors really care about that dx, dy stuff, right?
Yeah.
There's a reason why. It's because in higher dimensions, that actually, it plays a role. It actually is important. I want to find the derivative at some point on some surface. So take that, take this figure, for example. I don't know really how to define, using this as a regular definition of a derivative, I don't think it makes sense on just a slope. So here's what we do. I'm going to read from the slide. Partial derivative of a function of several variables is its derivative with respect to one of those variables where the other is held constant. So this time, you derive a function with respect to x or respect to y. So the example here, the partial derivative here is notated with this special d right here, and it says respect to x. So what do? I let every other variable be constant. I set it to be a constant, and what that means now is that my function, instead of a function of two variables, it now becomes a function of one variable, only x. Y is held constant. So the nice thing is that we know how to take derivatives of that. To take the derivative of that, we know how to take the derivative of that, and we can just simplify it. Geometrically, it looks like this. So I fix y. Here's the y-axis right here. I fix y. Suppose that it's an arbitrary value like this. And now this here is like a level curve, right? This is now a function of one variable, and I can take the derivative of it, and this is the slope. Here's the tangent line at this point, and I can get the slope of that, and that is the partial derivative at that point. Don't worry if you don't understand partial derivatives. There's only one thing you should know, which is not going to be on the next slide. Okay, let me take a quick break here. I'm running out of water.
Want to get you some more water?
No, I'm good. I'm good.
Sure.
Yeah. So, all right. So I'm going to talk about probably one of the most important things in like machine learning optimization stuff, and that is the gradient. So what is the gradient? It is a vector of partial derivative. So I know some of you guys haven't taken linear algebra, but a vector is simply just an array of numbers. It's just simply an array of numbers. And what the gradient is that, so we were talking about partial derivatives, right? All you do is just simply stack them in a list, going from in order x, y, z, and so on. So in this example here, suppose that our function is a function of two variables, x and y. Your function, your vector will be only dimension 2, and it will just be the derivative of f with respect to x at the first entry, and then with respect to y at the second entry. Don't worry about this notation here. There's only one thing you need to know, and so just a side note, right? Question?
Yeah, so like that slide over there. So you're saying that we have a function that pretty much takes all the inputs and then gets the partial derivatives of each input and then makes it into a vector column, like.
So okay, so let me just try to be a bit clear here. So when you take the partial derivative, you guys know when you take derivatives of a function and you don't evaluate it at a point, you get a new function, right?
Yeah.
So these right here, suppose that these x0, y0s are not here, right? When you take the derivative, partial derivative with respect to some variable, you get a new function. And the same thing with y, you get a new function. So what you do is that when you're done with that, you evaluate it at the point of interest that you're interested in. And then this becomes a vector of just numbers. It's just a vector of numbers.
And what are you going to do with them?
So I'm going to tell you what we're going to do with them. I'm going to tell you why this is special. So I want to just point out one fact first before we get to why we care about these gradients here. So I still remember when I took there are always memorable things when you take courses, like after you're done taking a course, even like after like a couple of years, you'll still remember a couple of things from that course. Like one thing, for example, is that when I took Calc 2, one of the most memorable techniques I remember is integration by parts. One of the most memorable, I have a couple of memories with Calc 3, like how the final exam was really difficult. But one of the things that was memorable to me was actually this statement right here, which I'm going to state. This is a very important statement. The gradient of a scalar valued function evaluated at a point points in the direction of greatest or steepest ascent. So what does that mean? Okay, so I'm going to explain the statement. So what that means is that we know that if you take the gradient at the point, you get a vector of numbers. This vector, so I know it's starting to get more linear algebra. So a vector has a direction and magnitude. It tells you where it's pointing at. So I'm going to give you a really easy example here. Suppose I'm on this hill here, and I want to find where the peak of the mountain is. So I look around, and I'm going to use my gradient, and I'm going to, okay, so maybe it points this way. So I see with my eyes that the peak of the mountain is here. So the gradient is going to point towards that direction. I know it points in that direction because that is where it's the steepest. Because maybe over here this is like, so it's low here, but here the path here is really steep. So the gradient is going to point in that direction. I think maybe I'm going to stay in this slide. So in the next couple of slides we'll explain why do we care about these gradients. So the previous theorem says, so the previous theorem also applies to multivariable functions. So what you can do, in one dimension, you took the derivative, find where the derivative equals to 0, and that was either minimum or maximum, and you conclude if it's a min or a max. You can do the same thing in higher dimensions. What you do is that you calculate the gradient, so it's going to be a list of functions. You evaluate each of them and try to find where they're 0. So you want to find where the gradient is equal to a 0 vector. The 0 vector is a vector of all zeros. And then that's how you can find the minimum. It's sort of like if you're on a hill right here, there's no steep form here, so it simply just points, it may just simply be all zeros here, or it simply points upwards or something. Now the thing is, again, this is not feasible for really complex functions. It'd be simple in your classwork, it'd be simple when you take Calc 3, but in the real world, some of these functions in real life, they're really, really complicated. So we need to use different methods for it. I'm going to now describe the method to you on how we actually optimize a function that's really complex. Spoiler, it's called gradient descent. So we know that this statement here, this statement there, the gradient points in the direction of greatest ascent. So if I'm at a hill or something, so I'm at slope, I know if I look at the top of the mountain, I know that that's a gradient. So if I want to reach the maximum point, if I want to go to the top of the mountain, I simply only have to take a step forward in that direction. And what I do is that I take a step, and then I try to find where is the mountain again, or where is the steepest slope. So maybe it may have changed. Maybe when I took a direction, maybe the steepest slope is maybe right over there, or maybe it's here. So maybe the gradient points in that direction. Regardless of its magnitude, I just take a step forward in there. I do it again. Maybe it's going this way. I just take a step forward. Eventually, I'm going to reach the top of the mountain. So maybe the top of the mountain is like right here. It points here. Okay. I take a step. Now I'm at the top of the mountain, and the gradient is now, it's going to be 0 around this point. So once it's 0, I stop. It means that I'm at a local maximum. Now we want to minimize loss functions. We care about minimizing our loss functions. So what do we simply do? Simply take the negative. So so the gradient points in the direction of greatest ascent, I just have to take the negative, just negate each of the entries, and that's it. And I just take a step in that direction. So maybe the mountain is over there, and let's say I want to go down the mountain, I want to go back home. I just look where the steepest slope is. Okay, it's steep right over here, and then I just look the other way. And then I take a step in that direction. You keep doing this until the gradient is 0, until it stops moving. That's actually how gradient descent works. And that's how basically, in a very light sense, how neural networks work. So now I'm going to go to the next slide. It's what this figure says here. So suppose I start here. The gradient is going to point towards here, this point here. But I want to find a minimum. So it's going to point this way, but I negate it, and it will point in this direction instead, this direction. And I'm going to take a step forward in that direction. That is called gradient descent. It's exactly this. So what's up?
So, like you said, when you reach the end of the steep, your local maxima is 0?
So the gradient will be 0 when you're at either a local min or a local max.
Okay. And does that mean anything to the neural network? Like what does it register? Like is it? So
it means that you have reached some sort of like plateau, and so that's one of the weaknesses is that if you were only at a local min, so it means what that means is that around the area, around this neighborhood, the point that you're at is smaller than every other value around it. But that doesn't necessarily mean it's a global min, right? Because you could be stuck here,
Yeah.
but the global maximum may be right here. So in some sense, so that's why there are other methods to help tackle that problem. Does that answer your question?
No, what I meant was like, okay, I'm at local min right now, like local min, not global min, but I'm at a local min or a local max. So that means like that is different. So it's an outlier, right? It's different from the other ones. So do I register that like, oh, this is something weird, or like?
Well, what's going to happen is that your algorithm, once it finds either a local min or a max, it's going to be, it's depending on how much you step, it may be stuck there. Now, and the problem with it is that when you're stuck there, you cannot conclude that this is the global min. You just know that around the area, it is this value you're at is the smallest around it, at least around this ball.
And it's up to the user how he wants to interrupt that out.
Yeah, it's up to the user. Now, the thing is that generally these algorithms are not, they're computers, right? They're going to make some approximation mistakes. So, for example, like maybe you may go, for some reason, if you get lucky, that generally doesn't happen. Suppose that you reach a local, you want to minimize the function, but you're at a local maxima. You're at a local maxima here. You're only there because the gradient is 0. You're going to actually leave that area really easily, mostly because it's like if you have a ball, right? If you try to balance it on this slope here, it's easy. If you move it just a little bit, it will actually start falling down.
Yeah.
So that's like that's one of those properties that it's quite unstable at this point. When it comes to like slopes like these, it's quite stable around this area. So it's up to you how you want to interpret it. So if you say like, okay, my algorithm has stopped, you have to decide for yourself if that is you're happy with this minimum and you think that your network has learned enough, or if you want to use other methods, other variants of gradient descent that can probably give you a better minimum.
On other data sets.
Or if on maybe other data sets too, or variations like if you apply, for example, augmentation, for example. I know that I saw a question. Yeah. Sorry about that.
So you have to use brute force in order to find the global minimum or maximum, depending.
So sometimes what you see researchers do is that they'll do a couple of runs. So instead of training the network once or training some model once, they'll do it a couple of times with random weights. And sometimes you may get lucky and that stuff. And people do brute force, for example, hyperparameters too. They do a grid search across the field of hyperparameters, and they just try to find which one gives them the best results. And they will do it a couple of times, not just once, but a couple of times. There are like other methods, like for example, cross-validation. They'll do a lot of runs in order to make sure like they actually find a minimum. So any other questions? Okay, so the main takeaway here is I basically try to intuitively explain to you what gradient descent is. So what gradient descent is that you simply go in a direction of, you go in the negative of for descent, you go in the direction of the negative of the gradient, and you just take a small step there. Generally, they're going to be small. They're not usually too large because you may, for example, for this curve here, you may, if it's too huge, you may go like this, a zigzag. You may go like a zigzag here if it's too big. Or if it's really, really huge, you may go upwards actually sometimes. Or it may not converge at all. So that's why generally the steps you take, this step, by the way, is called a learning rate. That's why they're generally small, like very small, like 0.001 or something. Okay. I do have an extra slide that I just skipped here. It's just an example. There's an example of where you actually don't really need to use gradient descent. And you can simply just analytically derive the solution of what parameters give the minimum loss, actually. And a really easy example is is linear regression. There is actually, you can use calculus, you take the loss function, you take the gradients and try to find where they're 0. You can actually find a formula for it. Given the x's and the y's, you can actually find the slope of this line and also the intercept of this line. It's just an example of how there's some machine learning models that are actually quite simple, like linear regression. But the moment that you go into any variation, like for example, logistic regression or neural networks, They don't have a closed form solution, so you need to use iterative methods to do this.
So you would use a simple regression if you have a two-plane, like pretty much you have two inputs
Not necessarily.
equally weighted?
Not necessarily. You would use linear regression if you assume that your model, if you assume that the underlying data has some linear property in there. So if you see some linearity, you want to exploit that property. And the nice thing about linear regression is that since the solution is a closed form, it's really easy to calculate it. It's just a couple of matrix multiplications. So, but the thing is that in general, for some data set, regardless of its input, like let's say if it's only 2 dimensions, right? Sometimes it may be nonlinear. Like if it's quadratic, for example, right? If it's quadratic, then you may want to use other methods to tackle that nonlinearity. So you don't want to simply say like, okay, since I have a small data set, I'll use some simple ones. It just depends on the data. We are done with the calculus here. Any questions about the calculus part? I am trying to pace my time here. Okay, so next step is linear algebra. So I know most of you guys don't know about this, but I'm going to try to keep it really simple because, to be honest, because remember, these the gradients and all that stuff, the computer is going to calculate for you. You're not going to do it by hand, which is why I'm not teaching you how to do the math and all that stuff. I'm just telling you the intuition behind it so you understand how some of these models work. If you wanted to understand it fully, you would go online, take a free course, or just use the courses at UCF. All right, linear algebra. It's coded building blocks and gears. I'll tell you why. So first we talk about, so how do we encode data in our computers? We usually use these things called tensors. So we'll get to that. These things are called building blocks. So we'll start with some vectors. A vector is simply just an array of numbers. The length of the vector is simply just its dimension. I'm going to go to a couple slides, and I'm going to tell you how you use this in real life. I'll tell you where you use this in real life, but let me just explain these things first. Matrix, simply just a two-dimensional array. It's just a two-dimensional array, a square of numbers. It looks like this. You have two axes, and they're usually referred to as rows and columns. So in this example right here, there are m rows here and n columns for this example here. You can actually, you notice this. We went from a line, something like this, sort of like a line. This is like one-dimensional. Then we went to a square. We can actually take this even further, and that's where they're called tensors. And those are generalizations of arrays. They're just generalized arrays. Tensors are multidimensional arrays. So scalars, just numbers, they're 0 dimensions. Vectors, they're one-dimensional tensors. Matrices, they're two-dimensional tensors. And then when you get to 3D, you can imagine them that they're just a cube of numbers. A way how I like to view it is that the next dimension is simply a stack of the previous dimension. So for example, matrices are simply just stacks of vectors. So these vectors here, they're column vectors usually. But what if I stack them this way, going in the right direction? Stacking them that way, I get this. Now what happens if I stack multiple matrices towards the wall, like this? So in this dimension here, there's this matrix. And behind the screen here would be another matrix. That's a 3D tensor.
So you would have like a box of matrices?
Yeah, you have a box, and it contains, let's say, maybe like 10 matrices or something. So it will be 10 by the size of these matrices. That's a good way to think of it. Just like imagine you have a box and throw some matrices in there, and you count how many of them are there.
So basically, you would have a position like A000, like that would.
Yeah. So this thing is going to increase. So instead of having two numbers here, there's going to be three numbers that index where you are on that tensor. And you can get to higher dimensions, of course, 4D and 5D.
You can make a 4D and a 5D.
Yeah, so by stacking them, basically, so you have a cube of numbers here, so I have multiple cubes. Then you can stack multiple of these cubes, and you get a four-dimensional one.
So you have a cube inside a cube?
You can imagine, like, let's say you have a box, and then you have this cube of numbers, and you just put them in the box, and you have another cube, put in the box. Now there's two of them, right? That's, you can treat as like a four-dimensional vector. Let me give you some examples where you can use this in real life, and maybe you'll be better understand. Okay, so it's time to talk about some data, all right? So where do we use tabular data? So you may have seen data sets where there's CSV files and they have many samples and many features. So for example, I could be one sample and I could have a vector that has some information about me. So maybe the height, my weight, how many calories I consume a day, or for example, my eye color, if you encode it as integers, for example. So I can have some features about myself that I put into a vector. Now, when I have multiple of these, suppose I get that information from all of you guys. There's probably maybe like 20 or I don't know how many of you guys. I can put them as rows. So for my data, I put it as a row vector, and it's here. And then for, say, some other person, I put it right here, 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 and so on. And it becomes a table. It's like an Excel spreadsheet. So that is where you see matrices. I'm going to skip this for a sec. I want to talk about images first. I can give you another example where matrices come into play, black and white images. So the way how images are represented in a computer, suppose I have a 10 by 10 image. Each of the pixels, they're encoded with 8 bits. So what that means is that each pixel is encoded with a value between 0 and 255. That indicates how bright the pixel is. So 0 would be black, 255 would be white. And I would have an array of those numbers, and that shows me at each pixel how bright that image is. That's how grayscale images work. Now, how do color images work? It's actually just, you may have seen videos on this. There are just some red, blue, and green channels. So in each pixel, there's a red color, blue color, and a green color. And each of them have their own intensities between 0 and 255. You can treat those as three-dimensional tensors. So you can have, for the red channel, say you have an image like this. Your red channel could be a matrix like this, a matrix of numbers. And then your green channel will be another matrix right over here. And then the blue channel will have its own matrix right here. So it's like a three-dimensional cube, like that. OK, so do you understand 3D tensors now?
So basically what you're saying is each pixel is represented by 3 categories, right?
Mm-hmm.
So like, and if you have a bunch of them, it becomes a picture.
So there's 3 channels, and if you mix up these channels together, these are matrices. If you mix them together, then you get those colors. Like for example, the yellow you see on your screen is not actually yellow, right? It's a combination of, I think, just red and green. I don't know my colors, so it's just a combination of the channels. So that's.
So basically, if you have 0, 0, 0, that means it's a black color.
Yes.
And if you have 255, 255, 255, then it's white. So if you, depending on those numbers, so if I have a 3 by 3 array or 3 by 4 array with all of these like different types of combinations, then that would make a picture.
Yes, exactly. Yeah. So like for example, if you wanted to show a red pixel, the order is R, G, B. So at the R channel, the red channel, I just simply make this as bright as it can be, so 255, and the rest I make it 0. And the mixture of them creates pretty much, in some sense, almost every color you want. It creates, I think, around 16 million colors? So that's usually how we see colors on a computer screen. So do you guys understand images now? How in computers they're treated, they're just 3-dimensional arrays on a computer. What's up?
So if you're talking about 3D tensors, right, with red, green, and blue, right?
Mm-hmm.
So where does the 4D tensors come into play?
So I put here that under color images that there are 4D tensors.
Yeah.
So let me ignore this part for now. See these things right here. So the height and the width, supposedly you have wallpaper, right? This would be like 920 by 1080 here.
Okay.
And then you have 3 channels here. So this here is the 3D tensor. Now, how do these color images become 4D? You have multiple wallpapers, multiple images. So let's say you have 10 images, then samples would be 10.
Okay.
So you have 10 wallpapers that are all 980 by 1080.
Yeah.
This would be 980, this would be 1080, and then this would be 3.
Okay.
Some libraries, like for example PyTorch, they like to put the channels right over here instead. TensorFlow, they do both of them. They put the channels over here, or they put it over here, but you don't need to worry about that. But the point is that this is just an example of color images. Now, it's actually not too bad, right? So let's talk about 5D tensors. An easy example is videos. So let's talk about how videos can be 4D, right? So videos are just frames of images, just going really quickly. So you may have a video that is, the resolution could be, say, like, 980 by 1080, 3 channels, of course. But maybe it may have 10 frames, maybe 60 frames. So if your video is playing at 60 frames per second, then the video would be 1 second long here. So your videos, one video would be considered a 4-dimensional tensor. Once you stack multiple of them, then it becomes 5D.
So if you have 60 frames per second, that's 1 minute long video.
60 frames per second. So that means if you have a 60 frame video, it's 1 second long, right?
Oh, okay. So if you have 3,600 frames, that's...
Yeah, yeah, multiplied by, yeah.
Oh, no.
So if you wanted a 1 minute video, yeah, then you need 3,600, yeah, 3,600. I don't want to be embarrassed with my arithmetic. Yeah, but yeah, so that's an example here. This is an example here. I don't want to use up too much time. Is it okay if I just skip this example here? I think, but you guys get the idea of what these tensors are like, right?
Yeah.
Not too bad, right?
Yeah, so they're pretty much like a fixed tuple, and then you just change the rows, and the columns are always the same.
Yeah. So yeah, they're not too bad and stuff. Okay, let's continue on, because it's right now 6:40, so I need to go a bit more quicker to get some more room for the Python people, right? All right, so we're not going to talk about what can you do with these things. So okay, so you have data, but you want to mess around with the data. So you need to do stuff to it. So you want to do operations on them. So we call them the gears here. So generally in neural networks, you're going to do something like this. You probably will have somewhere in the function a layer that does something like this. Output equals Rayleigh function of the dot product of the weights and the input plus the biases. So let me explain what these things are. There are 3 operations. There's a dot product inside here. This is actually matrix multiplication here. I wouldn't say dot product. It's matrix multiplication. This here is 2D. This is a matrix. The input is 1D. So it's better to call this a matrix multiplication. It's just that in NumPy they call it dot. You can use a dot function here. So you have a dot product here, and then you have this addition here. So the output of this, I'll explain why later, but the output of this is 1-dimensional. So you have a 1D vector plus a 1D vector, this addition here. And then finally you have this Rayleigh function, which is defined as the maximum of x and 0. So what that means is that any negative numbers, they become 0. Any positive numbers, you keep. So that's what this means here. Later on, you'll see why do we say like max 0 here, because this is a vector and this is 0. How does that make any sense? We'll talk about that later. All right, so first, we're going to break these down, these 3 operations here. So we're going to talk about the 2 easy ones, which is addition and Rayleigh. These are element-wise element-wise operations. Basic operations like these can be applied independently to each of the entries in the tensors. They return tensors of the same shape. So for example, if you have 2 vectors, they are 3-dimensional, 3 elements. If you add each of them element-wise, then you will get a 3-dimensional vector. And a very popular function is the Rayleigh function, which is that. It's a very common element-wise operation used in neural networks. Now, here's why. How many of you guys have taken, is anyone taking Intro to C?
Oh, yeah.
It looks like a couple of people have. You guys learned about for loops, right?
Yeah.
Okay, so let me talk to you about why Python, NumPy specifically, is actually cool in this case here. So how do you add all the numbers? Suppose you have a vector A and a vector B, and you want to output C. How would you write this in C to add 2 vectors up? You do for I, from I1, 0 to the length of the array, right? C of I equals A of I plus B of I, right?
So basically you would have a for loop inside a for loop, right?
No, it's just one for loop.
Oh, so you're just adding.
Adding each of the
yeah.
index-wise.
Yeah.
But the thing is that you guys will eventually learn complexity, right? But the problem is that you need to go one by one, and there may be n of them, maybe a huge amount, like a million of them. Imagine a human doing that. I have two vectors that are size 1 million. I need to add them up as a human. I have to do this. It's going to take forever.
Yeah.
So here's the trick. Here's the trick. How do you make that faster? I simply say I have 10 of them. I have two vectors, size 10 each. I hire 10 of you guys to add each of those numbers.
Okay.
That's called parallel. So that's called that's a parallelized operation. And if I just said ready, set, go, once you guys add those numbers up, it'll be really, really quick. So Python can do this. Python can do this operation really, really quickly. So they have highly parallelized versions of these routines. These functions here, they're called ufuncs. We'll talk about these later. It's sadly not in today, I think. Okay. So I'm just giving you a reason why you should care about Python. It's actually really cool. Of course, C can do the same thing, but you probably need more lines of code to do the same trick.
Trust me, you don't want to do this.
Okay, finally the last thing here. So it's going to be hard for me to explain this. So the dot product, it's between two vectors, just one dimensional. And how you do it is that at each of the indices, you multiply the two numbers together. You multiply the next two numbers together at index 2 and then index 3. You just multiply them together and then you add them up. The important thing is that it returns one number. Given two vectors, it returns a number. Okay, so now we talked about this right here, right? So there's a 2D vector here and there's a 1D here. This is matrix multiplication. So you're going to learn in linear algebra how to multiply two matrices. So like in this case, for example, if this was like AX and stuff. I'm going to try my best to explain it to you. How do you get a one-dimensional vector? I like to treat this product here as if they were multiple dot products. So you have a square here, and then you have a column vector here. I take this row vector for the matrix, and then this column vector, and I do a dot product. Then I do the next column, and then take the same vector here, do a dot product, so on and so on. And that's how it works. That's how matrix multiplication works. Don't worry if you don't know how to do that. It's not important that you learn about that stuff. But I think the most important takeaway here is like, how do you represent data as tensors? How this thing works here, it's probably best you get a course on it. Okay, it's almost done here. I'm going to summarize this information here. So we talked about a lot about calculus and linear algebra. I'm going to remind you guys where do you use this so that this knowledge is useful for you. Calculus, you generally use it for optimization, so gradient descent, and in neural networks there's this technique called backpropagation that you eventually will learn in core. Linear algebra, you can use it everywhere because you're dealing with data. So you're going to use it everywhere, but in specifically things that use a lot of linear algebra techniques like matrix multiplication, you'll see that stuff in regression, support vector machines, neural networks, principal component analysis. Like these have a lot of linear algebra involved with them. There's other, of course, things like random forest and that sort of stuff. But generally the data is just that's where the linear algebra is in sort of the data. These have a lot of linear algebra in them, and of course there's a lot of overlap between the two because like for example neural networks, right? You're going to use calculus, gradient descent, to find the minimum of the loss function in this case. So that's where you use calculus and linear algebra. But for you guys that really love math, it does not stop there. There's actually one thing that I don't have time to talk about, which is very important if you guys want to learn even more, and that is statistics and probability. A lot of machine learning models, they're motivated by probability. So for example, naive Bayes, there's this manifold learning technique. This dimension reduction technique is called T-distributed stochastic neighborhood embedding, TSNE. There's also Gaussian mixture models. There's a lot of other techniques out there. But you can also use many crazy mathematical fields also in here. I heard that apparently you can also use combinatorics, but I don't know. I couldn't think of an example. If you want to use graphs, like for example, you have a social graph, right? I could be friends with somebody on Facebook. Maybe two of you guys may be friends on Facebook, and that forms a social graph. I can perform operations on the graph and do some machine learning on it. I can figure out some patterns among the network, depending on you guys, on who is friends with what. So you can apply some graph theory, and then even some crazy math, even that's related to like some algebra. There's this field called topological data analysis. You can even apply topology. Topology motivates this method called uniform manifold approximation and projection. It's called UMAP. I'm looking into this method for my research, actually. I do research in manifold learning. Okay, so that is the math. And before I go to questions, I want to let you guys know that I got a lot of this material from this book called Deep Learning for Python. I absolutely love this book. I even own a physical copy of this book. If you want to learn more about the stuff, like, so I didn't tell you guys how to do these things, like how do you take the derivative and all that stuff. If you're interested in that, I think this creator here, 3 Blue Run Brown, is a blessing in the mathematical community. He makes the most complicated subjects so accessible to the world, and especially this neural networks video that he has. So I recommend this video here. A book that I didn't put up here is called Hands-on Machine Learning with Scikit-learn and TensorFlow. I love that book a lot too, but I forgot to put it in here. It's in the speaker notes. That's the end. Any questions? I hope that this was a good talk for you. It's time for some Python, which you guys are excited about. Thank you.
Thank you. Yeah, and so real quick, I wanted to say, Calvin mentioned that this was going to be up online, so that way you could get this deck. Unfortunately, the website is still under construction, but that's a story for another day. It should be up here over this weekend, which means that through the website, it's a portal to all of the content that we have. Otherwise, what I think I may do is after this lecture, I'll link this, so that way you guys have access to it. I'm just going to drop this on the Discord. So.
All right, so ready to get started in Python? So we're just going to go over just a basic introduction to Python, so just learning the Python syntax, all the tools available with Python, things like that. So we're just going to, we have a notebook on Kaggle for here, so we can all run it online, so you don't need to worry about like setting up the environment on your own computer for now. Although there's
like make mention where it's linked.
Yes, you put it in the Discord?
General.
Okay, so there's in the Discord, there's a link for it. Oh yeah, for if you guys are heading out, that's fine. Did you sign in?
Yeah.
Okay, great, thanks. Yeah. Have a good night. The link is in our Discord. Otherwise, I'll walk you through how to pull it up through Kaggle on its own. So first, we're just going to go to this. When you go to Kaggle.com, click the search bar, search up UCF AI bot, and it's going to be this users will come up. Just click the little duck. So click them, and then click kernels. Scroll all the way down. It's going to load more notebooks. So just scroll all the way down. So we'll see your. It's going to be this one, the Math Primer Python Bootcamp. Ignore that one. So let's click that. And then make sure you click copy and edit, because that makes so you can edit your own copy, because you can't edit this copy right here. So click copy and edit, and then it'll open up your own version of your notebook so you can use. Everybody followed that process and got the notebook up. Thumbs up. Thumbs up.
Anyone need more time?
Good. You guys get up front here? Good? Cool. All right, well, mine's still loading up. Okay. So, let's get started. So, as of any programming language, our first program we're going to run is to print hello world. So, and this is a Python notebook. So, what's cool is with a Python notebook, you can have like these information cells, which with just regular text, and code cells. So, what happens here is that we can actually run just blocks of code individually instead of having to run like a whole program at once. We can just type some code into a block and just run it by itself. So it's really nice for creating tutorials and stuff, which is all of our workshops and code are going to be on Kaggle on a notebook. Or they're called Jupyter notebooks. So our first line of code is to print hello world. So you can either press the little play button here, or you can just do Shift Enter and I'll run it. So and then an output will appear below the cell. So. First program in Python, hello world.
I want to make a quick note. So for those that are just very new to programming, you guys may have learned C, but there's actually a really big difference between like C and Python. So C is called a compiled language. So each time you write a program, you need to compile the program. It gets you a binary, and it's machine readable code, and you run it. The nice thing about Python is called an interpreted language. Is that you don't have to like sort of compile it. You simply just run lines of code and it just runs. So
Right. Yes. So we can So it just runs it without needing like to compile the program or anything. That it just runs it on the fly.
in some sense, it's like really
yes.
convenient and all that stuff.
Bonus thing. Python is built off of C, so it's pretty cool. But yeah. All right. So we're gonna get up and running. So the official documentation is linked here. So see the official document. And there's also another helpful guide if you come from a strong Java background. So those are just some more resources in there. There's also a block here to go. They'll help you install Python locally in your own computer, so you can use it and run it locally, so you don't always have to use Kaggle or something. So whatever operating system you use, you can click your appropriate link here. So you can do that after the meeting. Otherwise, we can just run it in Kaggle as we're doing here. All right, so let's start with, let me make this a little smaller. That's still good to read for everybody? That's good? Okay. So we'll start with just our very basic data types. So if, so like ints, we have floats, ints, and doubles and things like that. In Python, the nice thing about variable declaration is that you don't have to specify the data type, and that's awesome. You literally just come up with some random name, it equals some value, and now that variable is that. It's inferred what type that variable is, but you don't have to explicitly define a variable as some type, which is really awesome. So you can say, if you say x equals 5, then that implicitly that variable type is int, but you never had to define it as an int. So that's really nice. So we have floats, which are floating point numbers, integers, which are whole numbers, strings, so any type of alphanumeric data in a string. So in Python, you know how you have like a single quote and double quote, and like in like C and other languages, if you use single quotes, that's just for like specifies a single character, right? And double quotes would be a string. In Python, they're both the same. If you use single or double quotes, both of them define a string. You can use them back and forth. It doesn't matter. So you can use both of them. You have booleans, which true and false. Lists. So lists are like cool arrays in Python. So lists can hold any type of objects. It can hold integers, floats, your custom class objects, like anything. So it's just a list of stuff, and it's just really nice to use. Yeah, question back there?
So is it like a circular linked list in a way?
Circular. I don't know the underlying data structure on how it's stored, like in memory, but I think it is O1 runtimes to access stuff, so I think it's more. Yeah, I think it's better than that, than just a linked list. I know for accessing list values and stuff, it is O1. So by what I mean by O1, if you don't know runtimes, it's constant runtime. It's just like instant. There's like no like any type of runtime like needed to done to access the value. Question?
Can you go through finding like the Kaggle thing again?
You're on a Discord, so if you go to Discord and go to General Supplementary, the link to the notebook's right there. Yeah. You had a question for someone.
Would the list type be similar to an array list in Java? I haven't used Java.
Yeah, it would be similar. You can add, you can append, you can remove, you can do a lot of those similar array lists, which we'll show in a second. So yes. You got a question?
Can lists have multiple data types?
Lists can have different. Yeah, lists can have integers, strings, floats all in one list. Yes, which is pretty cool. So it's literally a list of whatever you want.
So they're called homogeneous arrays, but they can contain any type, not just one type.
So we got some, and here's an example here. So we have x equals 3, which is whole number, floating point, and then a string with Python. So in Python, you just type print in parentheses, and it'll just print whatever you want. So you can print x, which prints 3, prints a floating point, prints the name, which will print the string Python. So you have so in Python you can add strings together, and which will append them to each other. So if we take the name, let me use the pointer here. So if we take name here, add a space. So as you see, there's 2 double quotes and a space. and then we use strx. So what str is a built-in Python function that'll convert whatever is inside it to a string. That's all it does. So we take the string value of x and we add it. So then Python becomes, this combination becomes Python 3. And then also you don't need to specify, you don't need to cast data types when you're doing doubles and ints, which is super nice, because you know how in like Java or C, if you're trying to work with ints and doubles, you got to cast one or the other if you do division or something. Otherwise, it'll truncate and do a bunch of weird stuff. Python's like, I got you, fam, and just does it for you. So, so x and f are added together, and it keeps the decimal. So, any questions on? Oh, yeah.
What's the runtime for appending a string like that?
The runtime, pretty sure it's just O(n) for whatever the length of the string is. Yeah. All right. So, and I'm just kind of showing you right now. We'll get into we can mess around with this stuff a little bit more. Let me just get through all the data types here. So then we also have true, false. So this is with all of our Boolean logic. So like and, or, not, XOR and things like that. So in Python, true and false values are with capital F and capital T, not lowercase like in most other languages. So it's capital T and capital F. So it's a Boolean, so it's its own class. So what's nice is that Python, your and or doesn't use like the ampersands or like the vertical bars. You literally type and that's your and operation. Really nice. So you do T and F, which is false. T or F, which is true, not T, so that's false, and then T does not equal F, which is like an XOR, is true. So yeah. So very simple. It makes Python code really easy to read. It's pretty nice. So it's very. You probably heard the thing Python's like pseudocode, and kind of is. So that's the very beauty of it. And so yeah, that's all with Boolean stuff. I'm gonna get into strings in a second. And we can do some messing around with strings. Let me see, going into operators. Okay. So string objects here have a bunch of methods to help us manipulate strings. So we can capitalize a string, which will capitalize the first letter. We can convert it to uppercase. We can, which will right here, s.upper will convert it to uppercase. You can do the same thing with s.lower. So you have rjust, which is a right justify, which basically adds spaces. So like you're trying to print out some type of table or something, you can do that to make it easy instead of having to do printf percent 15f, and you're trying to keep messing with the numbers and trying to get it all work. So it's a little bit nicer here. You can also do the same thing with center, and you can do ljust, which left justifies. And then you can also do s replace, so you can replace some value in a string with some other value. And then a very useful function that I use a lot too is also strip. So strip will remove all the leading and trailing white spaces. And what's cool about strip is that you can also it can not only strip white space, it can strip other stuff. So I'll show you that. We can write that out in a second here. So I also have some other notes here. So as you can see here, we got hello, uppercase hello. So it looks like, so you probably count that. It's what is that? Rjust for 7. Yeah, so that also includes the so there's 1, 2, 3, 4, 5, and then 2 spaces to right justify it to 7. Sorry, center it to 7. So there's 1 space to center it in the middle. And then, as you can see here, when the world printed out, there's no white space after it. So let's see what some of the other stuff's in there. So if we print. So say if we have some type of input and that has something like this, and we want to get rid of that, well, we can just strip a string. Pretty cool. So by default it'll strip white space, but we can actually add in some type of string or anything like that, and it will strip all of that from the beginning and end. So I have a bunch of dashes, word, bunch of dashes, and then but I stripped all the dashes from it and just printed out by itself. It's pretty nice. And you can do this, and it doesn't have to be a single character, so if you have I want to strip hello from it, I think this should work. Yep. So like say there's hello, word hello, you strip the string hello from the beginning and end, left with word. So you can strip whatever you want from it. That's pretty nice. Any questions on that? Nope. Let's just show you lower real quick, actually. So we'll print hello, lower. So as you can see here, this will lowercase it. This is how upper will uppercase it. So, and I see I'm running the function right onto the string object. This is the same thing as like if I put hello as a variable name and then called s.strip or something, it'll do the same thing. I'm just skipping that step and just running it right on the string directly. So, but it does the same thing. All right. So that's string manipulation. So let's go into arithmetic operators. So pretty much the same in any language, but Python has a few niceties, extra ones. So we've got two numbers. You know, we can add, subtract, multiply, and divide, which is pretty easy. But what's cool is we also have a floor division. So if you do two forward slashes, it will divide the output and then get the decimal number and then floor it to the lowest integer. So that's really nice. So if you're trying to, if you just want to kind of lop off the decimal afterward. So that's something in Python that's really nice. Everybody knows what the modulo operator does? Who doesn't know what the modulo operator does? Okay. So yeah, this works the same way. We'll return the remainder after a division. And what's cool is, you know how like in most other things too, if you want to get the power, you got to do like math.power, do something pow, or you have some type of pow function. Well, Python, you do 2 stars. There you go. You just get it raised to the power. So 1 star multiply, 2 stars will take whatever your first value is, raised to this value. So super neat. And also, so one thing in Python you cannot do x plus plus. Can't do plus plus or minus minus. Yeah, sorry guys. Python doesn't like that. But you have plus equals, divide equals, times equals, minus equals, you know, all that stuff too. So yeah, it's sad. Also, if you notice, there's no semicolons either. So that's, you never have to worry about missing a semicolon. So Python, what it is, it's a tab indentation. That's how it goes by. So blocks of code are tab indented, and that's how you go, like what code goes under one block, which we'll see more when we get into functions and stuff. All right, so let's actually run this. Make sure we get the right values. Looks about right. So what was it, like, what were the values? It was 14 and 4. So 14 plus 4 is 18. So looks like right. All right. Any questions on that? Pretty simple stuff. All right, cool. All right, so now let's get to the some cooler stuff with list, tuples, and dictionary. So these are very widely used. They're very versatile. They're fairly efficient. They're not really efficient, but they definitely get the job done, and decent runtime. So let's first go over list. So list is kind of the same way you've seen in our languages, defined with square brackets, and each value in the list is separated by a comma. So can have literally anything you want. It can have objects, can have strings, integers, floats, you know, your custom class objects, you know, all in one. It doesn't have to be in separate, so that's really nice. You can throw whatever you want to a list, and it just works. TM. So let's define an empty list here. So this is an empty list. You can just make it as square brackets. You can also add in some values, so like 1, 2, 3. And then in our last example here, we also have 3 different data types. We have an integer, string, and a floating point number. So let's go. So we got a lot of code in this one. We're just going to go through it here. This is going to just be all the different type of list operations that we can do. And I also have I'm going to go over a few other ones we'll type out here as well. So 1, 2, 3, and yeah. So let's start with an empty list. So we have an append function. So without looking up there, what do you think append is going to do to a list? add something to the end.
Yeah.
Everybody agree? Yeah. So right, this slaps it right at the end of the list. So if we're going to append a bunch of values here. You also have pop. So for those who knows what stacks are, everybody knows what stacks are. Yeah. So it has like a word pop method, which works the same like a stack. So you can pop the end of the list. So pop works at the end. And then you can also print lists, so you don't need to have any special printing function or anything. You can print a list, Python will convert it to string and just print the values in the list for you. So no need to do for loops or anything to print the values in the list. You can also assign elements. So you can also access and assign elements using indices, just like you can with any other array. So 0 will access the first element in the index, so it's 0 index for these lists. You can assign the values. So another thing, what's really cool about Python lists, so not only are they so powerful as they can contain any type of data types, you can append really easy, you can add functions, you can also replace and remove at different indexes, or you can provide an object, like whatever you want to remove, it'll find it in your array and remove it for you. And I'll show some examples in a second. You can also do what's called index slicing. So instead of just doing 0, what if I want all the values between values indexes 1 and 3, which the end's not inclusive. So this is called slicing, which is really awesome. So if I want to start at index 1, and I want to go to the end index, which only goes up to end index minus 1. So this is inclusive, exclusive for the outside. So this will get value indices 1 and 2, the values are, which in this case will do 2 and 4. So the generic form of, there's also, with slicing, you probably noticed this -1 here. What's cool is you can negative index list. And what negative index do, they start from the end of the array and go back. So if you want to access the last element in an array, you just put -1, boom, you're right at that last element. And with slicing, you can access ranges of elements. So here are a couple, if you omit any like these numbers, it'll just go to the end or the beginning or the end of the list. So just having, yes?
So with like the -1, if you -2.
Yep, -3, and that'll be second from the last negative, yep. Yeah, you can reverse index the whole array. Yep. So if you omit like one of the numbers, it just goes to the rest of whatever the rest of the array is. So if I'm starting at 2, and my array list is my list is like 10 long, it'll go up to 2 to index 9. It'll just go to the end of the list. And same thing from the beginning. There's also a third option. So this comes from here. So this is the general form for indexing. You have your start index, your end index, which remember is non-inclusive, and a step. So you can instead of going step every 1 element, you can step every 2 elements, which you see here. We're going to copy this whole list, but skip every 2 indexes. So we go 0, 2, 4, 6, so on, until we run out of elements in the list. And so slicing can take a little bit of kind of wrapping your mind around, because it's very different. You can't really do that in most languages. So don't get too caught up on it. It's just simply we're just selecting ranges and a list. And in some type of array, we're selecting a range of values very easily, right in here, using this formula here. Any questions on list slicing? Yes.
Why does the first print list not include 3?
Which first print? This one?
Yeah.
Good question.
Because remember, our end index is non-inclusive. So we put index 3 in there, but it's only going to go up to index 2.
Okay.
Yeah, that's why. So remember that your end index is always, you only get the value, your end index minus 1. That's what it'll go up to. But the first index, the beginning, is inclusive. We'll include that element. Any other questions? Yep.
So if you put 1:2 in that example, it would just print out 2.
Right. Yep. It will just print the whatever value you're accessing. All right. There's also a delete operator. So there's a few ways to delete. So I'm going to go through all the code written here, and then we'll write some more on different ways to delete as well. So delete list li2. So list is now 1, 2, 3. So we delete index number 2. You can also add lists. So add list will just append on the on one list onto another, just like how you can append strings. You can literally take one list, another list, and just slap them together, and now you got one big list by just using the add operator. So that's really nice. So you can do the same thing. You can also these two operations are exactly the same, right here. You can add two lists together using the add operator, or you can use a method in the list called extend, because it's exactly the same thing. Just extends one list with the other. Just appends them on the other list onto the first list. And here's all the different ways to remove and insert. There's all these functions here to access different arrays and remove elements and stuff. So remove 2. So this isn't removing the index 2. This is removing the first occurrence of the value 2. So it actually will look through the list, find the first value of 2 that it finds, and just delete it from the list. You can also insert, which insert at a specific index. So at index 1, we're going to insert the element, the value 2. Everybody following along? No questions? Cool. Oh, okay. Scared me there. So what's cool is too, if you want to check if something is in a list, you don't have to. Python does not force you to iterate through the entire list and find a value and do if statement. You can literally say, hey, is this element in this list? And it just prints true or false if the element's in there or not. That's all you got to do. And it can be whatever element you want. Is 5 in the list? 5 is in the list, so you get true. Also, you have the len function, which gets the length of any object. So this works for dictionaries and other things that we're going to see, but len will get the length of the whatever it is. In this case, the length of our list. Also, remember, list, if you set the value of, if you just try to create, like if you want to create a copy of a list, do not do this, because all this is saying, this is like the same pointer to the same list. So when you do new list equals li, both of them, so you have like new list variable and the li variable, both of them access the same array in memory in the same list. Does that make sense? Yeah.
Does it happen with variables that are like of type int or bool?
It doesn't matter what's in the list.
If you have a variable x and a variable y that are integers, and you set x equal to y, will x point to y?
No, this is just for lists.
Okay.
Yeah. So if you want it, so in this case, if you want to copy, so let's run all this and we can see.
I wanted to expand on this question. So certain primitive types like integers and what you see later like tuples, the primitive type like strings and that sort of stuff that I don't want to introduce this one, but they're called immutable. Those don't have that sort of property where if you like have them two equal and you change one, then they change to like extends, I think, like their pointers and all that stuff.
Right.
So primitive types, you don't have that thing.
Right.
So you only have to be careful about like
lists, dictionaries, things like that. Yeah.
Lists.
Right. So this covered a lot with lists. I mean, this is really everything. I want to expand on a few things in here. So you can see all these values here. So this is all the output of all this stuff that happened here. So you want to check it for yourself. So I created a new cell block. So if you go to insert here, you can click a code cell, and I'll insert another code cell. I'm just gonna do a few more things. So to expand on so if we have like another list here, I'm gonna create. Oh, you can't do lists. That's an actual name. We'll just use li again. So we'll just create a list of integers. So you can do so we just printed out like 5 in thing and just printed out that truth value, but you can use that in if statement. So which we're going to cover if statements in a second, but I want to make sure I cover this. So you can do like if like the value 10 in li, and then we can run some code. So this to show you that like this is like another conditional, like in means if this value is in whatever this data type is. There's also, I think we covered remove, extend, delete. All right, just want to make sure all that was covered in negative. And do you want to see more examples of maybe slicing, or you guys are good? Good? So yeah, you can. I highly encourage you to mess around with like the code in here and see what outputs and stuff, so you can get a feel for it. All right. So list comprehension. So So what's even cooler is that, we have lists. Python's like, look, you don't need to create for loops to iterate through them, to print them out or anything like that. We also don't need, we can use for loops. We can actually build it into the list and do one line of code to actually iterate through some type of iterable value and populate a list with those values. And that's list comprehension. So in here, we can do expression. So we can say, which is whatever we want to type. For member and iterable. So iterable would be some type of like list or something, or whatever we're iterating through. And we can actually populate a new list just like that in this one line of code using the for loop. So we have the expression, which is this whatever type of calculation or math or anything that we're trying to do that's then populated into the list. So whatever expression, the result of this expression is populated into the list, put into the list. We have member, which is just whatever the current value is in this iterable. So iterable is a list, set, sequence generator, any other type of object we can iterate through. It's like an array or just something we iterate through. And member is every value in that array. As we go through, we'll change to whatever value we're currently in that array. So let's see how that's done. So we can say we're going to populate a list. We're going to say I times I for I in range 10. So range is a built-in Python function that allows you to get you a range of values. So range 10, what do you think the values will give you? Just shout it out. What do you think?
0 through 9.
0 through 9, right. So range 10 will give us, it starts at 0, so and goes to 1 minus whatever range is. So range gives us an iterable to allow us to iterate and get the value 0 to 9 really easily. So if we run this in one line of code, we populate a list with the squares from 0 to 9 of the values. So 0, 1, 4, 9, 16, 25, and so on. So, and that's just in one for loop. So now we can even extend this even further, this one-liner. We can also add a conditional to this and only populate based on condition too. So we can say, so after this whole for loop here, we can say if some type of conditional. So it'll only populate to the list if this conditional returns true. So we have for I in sentence, if I in A, E, I, O, U. So when we iterate through a string, it iterates through every character in the string, one by one, including spaces. So spaces are characters too. So we iterate through those too. So I, it basically represents wherever the current letter we are in a sentence, and this list is going to be populated with I if this character that we're on in this character that we're currently on in the string is in A, E, I, O, U. So we use this in operator, but instead of using it for a list, now we're using it with a string. And when you use in operator with a string, it just finds it basically does string comparison against the whole string. So if you have one character in AEIOU, it'll check each character in the other string and see and compare it to this character and see if they're the same. So if I wanted to do but I can also extend that to strings. So let's see here. So we have E. So this is so if we iterate through. Does it iterate backward? Kind of weird. I and A, E, I, O, U. But I got E first. The first one's O. Kind of interesting.
The first one's U.
Oh, I'm just stupid. Okay. I see. So E, O, E. I don't even know English. This is why I program. All right. So, right. So as you can see, we got all the values. So let's do. So we can say if. So I just want to show you another example. So we say this string hi is in. Okay. So you can also just say hi. If hi is in hi are you, we'll basically take this string, start here, and then start comparing like this until it finds the string, or it goes to the end and doesn't find it. So it's the first two characters here, so it compares that. So this code runs and prints yes. So you can just do that in an operator with strings as well. Whoops. All right, any questions on all that list comprehension? Did I blow anyone's? Ah, okay.
If I want to make, I don't know if you said it after when you said about one list pointing to the other. If I didn't want to make a copy of that set list, would I have to run a for loop, or is that like something else?
Oh, to copy a list?
Yeah.
Okay. Yeah. So say for example, I have this list squares. If I want to copy it to a new thing, there's a few ways you can do it. So a general way is to do square is to type the array name, and type the array name and then put a single colon in it. So you remember this is our array slicer. So basically, if you put a single colon in an array slicer, it's basically the whole array. But in this case, when we do this, it's slicing this array, it's creating a new copy, and then now that new copy is set to this variable, so that will copy it. I think there's a copy function. Calvin, you know, is there a copy function for a list?
Yeah, I think you can use do list.copy.
Yeah, let's try that. I'm pretty sure it says list.copy, so let's see. We'll go ahead and print that out. Yep, so you can just also do the list.copy, or you can just do, I'll show you the other way that I did it, with the slicing. Works the same way. And so, and just to confirm that it's copied, we'll say new squares 0. So as you can see here, it's a copy. It didn't change the first thing. All right. So we covered the list conditional logic and list comprehension. Does anybody like the syntax and how this works? Yeah, it's pretty nice. I mean, don't get me wrong. There's some performance sacrifice for this stuff, but honestly, it's okay. This stuff, it makes life really easy. And Python's very powerful, and there's tons of packages to do anything you could ever want with it. So it's pretty nice. All right, so now we're going to go to another type of iterable object, tuples. So tuples is pretty much exactly the same as a list, except you cannot modify the elements once after the tuple is created. So if you create a tuple and it has a bunch of values in it, you can't change those values, you can't do anything. It's just a static. It's basically it's just a constant list, and you can't do anything with it once it's defined. And that's different in a list because lists, as you saw, we can modify the elements, but in tuple we cannot. So in tuple, you can have tuples of list. You can have lists of tuples with those tuples with lists inside, and those lists have tuple. Like you can go as deep as you want. So I mean, there's no end to how crazy that can get. So yeah. Let's see. Am I gonna? Oh no, we don't end until 8, right? Yes. Okay. Thank you for coming. So yeah. So we're just going over to this is the same like some string, or these are characters. Technically they're characters, but they're actually stored as like strings. There's no character data type in Python. Like they're just strings. So we have a tuple. So tuple is defined with parentheses. So yeah, don't confuse it with like a function call or anything. If you just have like parentheses like this in Python, that's a tuple. That defines this type of data structure. So as you can see here, we can access it the same way using index, using brackets, and then index to index access. And then also, you can do the same thing with lists, but tuples I can count. You just count how many occurrences of the character I appear in here. So 3. But yeah. So if we try to say, hey tuple, it's time to change your value, and let's say val. We're gonna get a type error, and it's telling us, hey, you cannot item assignment, you can't do that. So. All right, so we got 2 more. We got sets and dictionaries. So we'll cover these pretty quickly. So sets is pretty much it's an unordered collection of items. So it's like a list. And they're immutable, so that means you can modify the elements in them. They're not like tuples. But what's cool about sets is that there's no duplicates. So if you try to store duplicates, you can't. There's only every value is unique. So what's cool is, say if you have like a list that has duplicates, you can turn it into a set, and then Python will automatically remove all the duplicates, and then you'll just have to set up all the unique values inside a list, which is really nice.
So for example, if somebody gave you a question and it's like, given a list, get all the unique elements in this list, it's literally just a one-liner in Python.
Yeah. So we can also do we can add values to it. We can update, which basically just you can add multiple values to it. That's what all update does. You can also remove at specific indexes. So yeah. So and also if we create another set, and I think if we just try to put duplicates in here, it should come out. Yeah. So we start out with the set 1, 2, 3. We add 4. We get 4. We add 2. The output's exactly the same after we add 2 to it because there's already 2 in there. Update 3, 4, 5. We'll add 3, 4, 5 to it, but since 3 or 4 are in here, our set is only updated with 5. We can also remove, add a certain. Or no, is this index? No, this is not index. So remember, remove is not indexes for objects. Sorry. To remove, if you want to delete at index, use the del operator. But as we saw before with list. But remove 4 will remove 4 from this. So in this case, 4 gets annihilated. And then, so I tried to create a set with duplicate values, and it ended up just moving our duplicates. But do you see something interesting? Like I created this set. What happened to the values down here?
They got sorted automatically.
Yep. So, yes, they got sorted automatically. So that's something they do. I'm not sure if it always does that. I think it always sorts, depending.
How does it work with other types, or if you have like your own?
So most classes and stuff you can implement like a comparison function to tell Python, kind of like in Java, you can tell Python how to compare objects of this. But if there's multiple objects, I think it just sorts. I'm not too sure if you have like different types of objects. I think I'll just pick one and then just like put all. So if you have all objects of the same class, we'll kind of group them together into one. Yeah.
How would you convert an already declared list into a set or tuple?
All right, that's pretty easy. So let's go over that real quick. So let's see. I got. So let's do. It's very easy. So you know how we have str to convert stuff to strings. So you have the same thing with the literal name list and set. So we'll say list, and we'll call it my set, and we could print tuple my set. So as you can see here, it's now changed to brackets. So it's changed into a list. It's parentheses. Now we got a tuple. Very easy. Thank you guys for coming.
Is that like casting in a way?
Yeah, I mean it's kind of not really casting like you see it in other languages, but it's basically just converting your types.
Okay.
Yeah. So and I'll show you the example real quick. So let's say if I have, let's just change this. Let's just copy this real quick. So let's write this out, and we'll say this. We'll call this a list, and then we're gonna print the set of this. As you can see here, let me print the list real quick. So you can see here, this is the list version, so it's exactly how I wrote it out here with all our duplicates. And when I convert it to a set, boom, automatically sorts in, removes duplicates. Yep.
I'm going to throw give some more value to sets. So like what he has shown here, you may think like, okay, so they can only do one thing that's useful, which is just remove duplicates. But there's one thing that I like about sets in terms of like performance-wise. And so for example, in list, if you want to check if something is in a list using in, that's so you guys have to know about all that stuff. So you need to look through the whole list. So that is linear time. You need to look through the whole list.
Is this
If you try to check something in a set, it's constant time because it's based on a data structure that you'll learn in CS1. It's called hash tables. So you only understand why it's all important when you're in hash tables, but that's the reason why sets can be useful, which is when you use in, it's really, really fast.
All right. So, did you have a question?
Yeah, so perhaps I missed you saying this. So this says here that the set is unordered, but this is actually ordering the numbers?
So it says an unordered collection. So I think because there are ordered to themselves, but in it when you're in a set, you don't really have. There's a different explanation for that. I'm trying to think. I'm trying to remember what it was. So it's just because since a set has no duplicate, the values inside, while yes, Python will sort them. It depends on what it does, because if they aren't able to be sorted, they're just kind of just a collection of items, right? And so, and that's the thing with sets is that you use these functions to add and get elements and delete elements. So in this case, the reason why they're unordered is that index has no meaning with sets. So for example, as you can see here, I'm not doing my set brackets index 3. You can't do that because there's just no index. That's what it means by unordering. That's what I was thinking of. So yeah, so the elements are ordered, but there's no indexing. There's no order to the actual set itself. There's just a collection of elements. I don't know who had their hand first. Yeah.
So they have no index because of hash tables, right?
Yeah, I think they do use hashes. I'm not 100% sure. You can look up on the documentation for the underlying data structure that runs that, but that would make sense if they were hashed. Yeah.
So you mentioned that in order to automatically sort sets, Python uses some type of comparing function. Wouldn't that be kind of expensive then?
I think it's best if we maybe probably get back to you on that.
Yeah, I don't know off the top of my head. I would have to read up the documentation for the actual underlying code that runs that. Yeah?
And since the sets are like dynamic, wouldn't you have to rehash that thing? Like every time you would
I mean, again, that's like the underlying data structure on how that would work.
Yeah,
And
so like the thing is that like there's probably a lot more computer science theory behind these things that you don't get to learn in like CS1 and stuff. So it's better, I think, like for these challenging questions and stuff, it's probably best that maybe we'll try looking up the answer. We're probably gonna do the same thing as you, just Google it. But yeah, it is interesting.
So this is cool. What's another cool thing about sets is that you can actually do some logical operations on it, like and or. So this is something that I actually is really powerful. So and this is where we actually don't use or, like the actual text OR. We use the vertical bar. So this or means is basically like who knows anything like barely like just a little bit about set theory, where like intersections and unions. Has Eve heard of that before?
Wait, could you repeat that?
Intersections and using sets like you've seen maybe in like a math course or discrete course.
No.
Okay, that's fine. So you don't need to do that. But this is it. But if for those of you do, this is exactly what's happening here. I can union or
Right.
two.
Yeah, essentially what's happening in a union is it's looking at those two sets, right? And it's taking all of the elements
Yeah.
of both, right, and outputting those.
So sets you can think of like sets, and you've seen in your math classes. You've seen them.
Right.
But yeah, this OR is two sets. So basically, all the values that. So let me make this set. Let me just make this set easier to look at. So it ORs the values in here, and then creates a new set. But 5 and 3 are already in here, so it just ends up printing the same thing.
So you can
So
do
let's
intersection too.
do the intersection. Yep. So intersection is just one ampersand, and there we go. So now 3 and 5 are both in here, so we get the intersection, and we'll just delete the element 5. So our union still worked out because 5 is in here, or 5 is, even though 5's not in here, 5's in here, so it works out. You get this whole list. But when you intersect, both of these only have 3 in common, so you only get 3. So that's really cool. You can
I've been doing Python for probably like a year or two, and I still learned something new.
You didn't know this?
I didn't know about that.
Yeah, this is really cool. And you can do like, if you want to update this variable mset, you can do bar equal sset. And then we'll just print that out, and it does the same thing. It updates the value on mset. So you can do bar equals, or you can do ampersand equal to do those operations. Yeah.
But I use the dot. They have like a dot intersection and dot union, I think.
Yeah.
Yeah.
Yeah. I didn't even know that. I knew it only had these two. So
They have methods.
Yeah.
Methods, yeah.
All right, so we're almost done, guys. We're just gonna cover dictionaries and then just. Well, actually, we're not almost done. We got a lot.
Might be able to leave some of that.
Yeah. So dictionaries. Well, I'm just gonna try to get through really quick because I know we're approaching late. We had a lot in here. So dictionaries. So they're basically like hash sets that you've seen maybe in Java or another programming language. It's basically a mapping of keys to some values. So your dictionary, that's called myDict. Let's see. So 1 to Apple. So basically 1 is the key and Apple is the value associated with that key. And again, your dictionary can have anything your heart desires. It can be objects, lists, values. You can have lists and dictionaries inside your list and dictionaries, inside your list and dictionaries.
As long as the key is immutable, that's
Right.
the only restriction with lists. Dictionaries.
Yes. So dictionaries, the key has to be immutable, meaning you can't have a list as an actual key. It can only be like some type of string or
Or a tuple.
integer or a tuple, because remember tuples are immutable, so you can actually use tuples at keys. I think it's mentioned down here. And you can also so you access the key. So this 2 is not an index; it's the value 2. This is the actual key. This is the value. So in this case, how we're accessing the dictionary. So the dictionary name maps to the value John. So we can actually brackets. We just use the brackets again to access elements, but instead of using indices, we're using the key value. And then we can print it out. You can use the same deletion operator to delete elements, or you delete the entire dictionary. So you can actually, you can do the same thing with list comprehensions as dictionary comprehensions. So you can still run like these for loops. And so what's cool is that, so you have key and value. So you can actually, you can populate a dictionary with key value pairs using a for loop and a conditional all in one line. So that's really sweet. So let's just run this cell here. As you can see here, we could print the dictionaries and we get the values right here. So we have 0, 0. The square of 2 is 4, and the square of 4 is 16. So we're mapping even numbers of squares. So, yep. You can also a side note here, the truth value of an empty list or dictionary or set is false. So if we do, so that we do not print yet, the truth value of an empty list is false. But the truth value of a non-empty list is true. So just so you know, you see it's an easy way to say if the list is empty or not. You can do the same thing with dictionaries and sets. So control flow. So now we covered all the basics. We're going to cover all our ifs and functions and classes. So get into OOP. So try to get through this quickly. And this will also be recorded too if you need to look back if we're going too fast. All right, so really easy. So we have our if statement. You saw me do it before. You say if some condition. Don't need parentheses around your conditions. The only thing you need, you use colons to actually specify the end of the if statement conditional. And then as you can see here, everything's indented under here. So remember, Python is indentation specific. So every indentation, your indentation has to be consistent with every block. So you can use however many indents or spaces or tabs you want, but it'll have to be consistent across your entire file. Otherwise, Python will get mad. So you just have to make sure your indentation is correct. So sometimes it might be harder to see, but I mean, really, it's pretty easy to tell what code goes where, as long as you have a ultra wide monitor. If you have really long lines of code. So if we run this, say num's greater than 0. So you have the same logical operators: greater than, less than, greater than or equal to, less than or equal to. 2 equal signs for is equivalent. Exclamation point equal sign for does not equal, which we saw earlier. So all those same logical operators of comparing two values. All right, so we'll go into loops. Any questions on that? Good? All right. So loops, so we got while loops, so very simple. Again, we have while some type of condition, colon, run this stuff. And so, yeah, not really much to comment on here. While this condition is true, perform these actions, update the counter. Make sure you update your counter, otherwise you get some infinite loops, which isn't fun. So the sum from 0 or from 1 to 100 is 50-50. Pretty cool. For loop. So for loops, so the way they work, we don't do by indexes by default. By default in Python, when you use a for loop, I see before, we have some type of list or iterable, and we're saying for value in list, or whatever iterable we have, this value would represent each value in this number as it loops through, and we're gonna perform some operation, and this will iterate until whatever this is empty, like it went through all the elements. If you want to get the index, so if you want to get indexing too, there's a function called enumerate. So if you type enumerate and you run this inside a for loop, this will return two values. We'll return the index and whatever the value is at that index. So what's cool in Python in the for loop too, and you can actually have multiple you can have like multiple values that you're iterating across. So you can have like 2 or 3 lists and iterate all across all of them at one time. You'll only iterate to whatever the smallest list is. Once the smallest list is exhausted, it'll end the entire loop. But yeah, so you can iterate across that.
An example where you may see this type of, where you like say for I, j or something like that, is where if you have like say a list of tuples, and maybe you know inside the list the tuples are only size 2. So you can take that to your advantage to make it really readable.
Yeah, so then this for loop here, I print the index, so 0 to 5, because we got 6 values in our array, and then our sum. There's also other functions like zip and stuff to do some other things, but I'm running out of time here. You can look those up. So zip will basically allow you to do what I just said before. We can have multiple iterables and run through them at once. So we have break statement, does exactly what it does. The end breaks. So we'll just break it. If this statement is reached inside of any for loop, it'll just break out of this loop. Continue. So basically, if continue happens, it just skips the rest of the code that happens here and goes on to the next iteration in the for loop. Thank you for coming. All right, so now we're going to get to OOP, functions and classes. So to define functions, again, we're using these colons. So any function is just, remember, we don't define return types or data types or anything like that. So we just use def to define a function. So def, whatever a function name is, and then our list of arguments. Our arguments are not typed either. So you can specify types if you want to. So in your return, you can just return a plus b, whatever you want. So just a side note, you can define types. If you want to force something to be a certain type, you can use colon and then whatever data type you want.
Fair warning, you know that notation only works in specific versions of Python, I think. Like, I think that only works in 3.7.
No, it's before 3. I mean, I think at least Python 3 supports it. All of Python 3, I'm pretty sure. You would have to look it up. Python 2 is dead, by the way. Don't ever use it. If you see it online, don't use it. Python 3 only. Yes.
Are values inside the function passed by value or passed by kind of colon?
They're passed by value. Yeah. I don't think you can specify. I think lists, they might be passed by reference.
Mutable things, they will be passed by reference.
Yes, yeah.
They're like pointers in some sense.
So they're automatically passed by reference if they're immutable. If they're not mutable, then they're passed by value. Yes.
That's interesting. I didn't know when you do sum2 on 2 characters that it just joins them together. It just outputs the 2 characters.
So if we do sum2,
rather than like the ASCII values.
Well, let me just try doing like defining something that aren't ints. It's going to get, it does that. Hey, I specified the data type. Maybe you're right. It should automatically thing.
Well, that's defining them, so then you want to print those 2, right?
Well, no, I'm pretty sure it should raise an argument or raise an error if these types don't match. Maybe there's something else you need to add to it.
So here's an example. So suppose that let's say you don't know about this trick with the int
Right.
and stuff. So if you wanted to make sure that your input is an integer, you can use the search statement. So you can say assert type of A is int. So you want to check the type. So to check the type is use type, and then you can just say if type. You could probably use is int. So you check if type A is int or blah blah blah. Then you can just raise an exception, or you can use an if statement. Or the way how I would do it is say if you want to raise an exception, then you use assert.
Right. So or you can do assert, which will raise exceptions, or just print, or you can just have it do something else. You can use the type of something, and it'll do the type, and you can compare it. So we'll try that print. Sum to. Just prints now. And then returns none. So if you just do return, it just returns none, which is like the null for Python version.
Also, if you don't each function, you don't have to return anything. You don't
Right.
have to put the return function,
Right.
but it implicitly returns none.
Right. So, and then you can also, so instead of doing does not equals, you can type out the English words to make it easy. You can do is not. And this is the same exact thing. Work the same exact way. So you say is not in. Like it's just not in it. Yeah. So. It literally is pseudocode, yeah. And you can also define default arguments. So b equals 3, if you do sum 2, it would do 3 plus 5. So default arguments. So what's cool is that you can also do, so Python and function arguments, it's crazy what you can do with these things. So I can't cover everything here, but pretty much you can actually get a variable amount of arguments and iterate through those arguments using this star sum. You could basically get like a list or something, or it's not even it's not an actual list data type. You can literally get like just like a ton of arguments like in variable, and then you can use them. Yeah.
I know they have what you're describing in JavaScript as well.
All right. Yeah, I'm not too familiar with JavaScript, but yeah, I mean you could do stuff. You can also do this thing with with something else I'll show you in a second. But yeah, so you can get a different amount of sum. So with here in this case we had 3 arguments. Maybe we just only have 2 arguments. Yeah, so it will still work for any variable amount of arguments. So you can also use keyword arguments. So there's positional. So there's 2 type of arguments. You have positional and you have keyword. So positional arguments are stuff that rely on the position of how you pass it, and keyword doesn't matter what position it is. You specify, I want the argument B to equal 2 and A to equal 1, and so this will change the values in here. So maybe we'll see if we divide. It'll show better. So if now we say A equals 2, B equals 1, change that around. All right, I'm gonna skip over lambda. You can read that. It's just a way to like define functions like in one line, but I want to get through classes here. We're running out of time. So this is how you define classes. Use class. You define the name of it and a colon, and then all this stuff is in the class. So the thing about classes in Java, there is no private or public or protected variables. It's just a class, and it has all the stuff in it. So there's no really notation that a variable is private or public. You have your constructors. So this, in this case, will define a class. So this is a class method called function. So you do my class add function. We'll run it. This is a class variable a equals 10. So you do my class dot a will access this variable and print the value. So constructors are defined a little bit differently. So you don't use the class name. You literally type underscore underscore init underscore underscore, and that's your constructor that runs. So you notice this thing self. You're seeing this here a few times. So what this self is basically every function in your unless you define them as a static function. Has this first parameter self, which basically allows you to access, in maybe Java and other languages, you have like this, dot, that's what self does. But it's passed as like a function argument. It's always your first function argument. So you do self dot, whatever value or function you want to access will access the function in that instance of the object. So it's just like the this operator. So this is our constructor. So self num equals 0, self dot num equals num. You just define it. So you do self dot num, that defines a class-wide variable here. So self dot num equals num. So every time you run self dot num, you get whatever that value is. So my class dot num here returns 12, which we called in our constructor here. So we have inheritance. Let me see. Oh, inheritance is the last one. So inheriting, you don't have to do it. You don't have to type extends. You don't have to do anything. You put in parentheses after the class name, whatever class you want to inherit from, and boom, you just inherit it. The main thing is that so in this case we didn't need this. So it also supports multiple inheritance too. And does everybody know what inheritance is? Okay, good. So there's another thing. You've probably seen this if you know Java or other things. When you're inheriting, you don't always have to do this, but say if you need to pass some stuff to the constructor of the superclass, you need to do super, I think it's, I can't remember the syntax. Is it self, is that right? I can't remember. I can't always remember the syntax for super, but basically you use the super keyword in order to run, in order to initialize whatever your parent class, whatever variables you stuff you need, you can use that to call the constructor. I just don't know which way to order to, and I don't want to look it up right this second, but you can use super for that. In this case, you can omit it because your parent class in this case doesn't need anything. So, but yeah, we can run this and we can show the inheritance. So we do D is a dog, display dog features, and we also display animal features. So, yeah. All right, so we're finishing just right on time. We have a.
You might have a few announcements, whatever you're done.
Yeah. So, well, real quick, does anybody want me to cover anything that I covered so far? Want me to go more in depth or see something else on it, or anything? Yeah.
I just want to ask one question. So there's no way to make a method private, let's say.
No. There's one thing you can do. I mentioned static methods. So say, hey, I don't want this function to be a static method. I mean, it doesn't matter what object it is. It does the same thing. You just do, so this goes into function decorators and stuff, which I'm not going to get into, but you can do @static method, and this defines this method as a static. So def. So you don't pass self to it, and so this defines it as a, so you
Let me help explain this.
So what I can, well, I'm still going.
Yeah,
One
sorry.
second. So what happens here? So static method, you don't pass self to it because a static method in the class means it's not object specific. It's just like a static method that always works no matter what. So no matter what object I have, when I print stat, I always get the same output.
So yeah, to expand on that, so one way you can use static methods is you can, instead of having to instantiate the dog class or do the d equals dog, you can just simply say dog parentheses and then do, you can, I think you can just do dog dot stat, I think. You don't need the parentheses for dog.
Yep, you know.
You don't need the parentheses for dog because when you put the parentheses, it instantiates it.
So you know, you're saying you just do dog dot that? Yeah.
Yeah, so you don't need to instantiate the object
Right.
for static.
So we're calling it right from the class. We didn't even instantiate an object, and we're still running it. Yeah.
And to also expand on your question, so you were mentioning about like private. So there's no such thing as private, but there is a convention
Yeah, it's still recording.
that people put
Warm this
underscores
up?
at the beginning of a variable to indicate that it is private. It's telling the user like don't actually directly access this.
Right. But
there's no way to force the user to actually
Right.
They can still access it, but it's more of a convention to tell the user like be careful about this.
yeah, so you're talking about underscore in front of the names?
Mhm.
Yeah, so that's just a convention. There's actually a cool thing, I really want to say this, so you can import functions from other files. If you start functions in other files with an underscore and then say import all the functions from a file, functions that start with underscore are not imported by Python. So it's already convention and also built in that underscore defines an internal function that only should be. It's only available in this instance. Yeah.
Right.
So Justin had a few announcements before we wrap up. So.
Yeah, hey, I don't want to keep you guys any longer. Thank you for sticking it out.
Yeah.
And it's a shame I didn't get to say it to the people who were here. So this workshop and this kind of thing that we went over was a lot less interactive than our next ones are going to be. And so definitely come out next week and check out our Getting Into Research if you're not in research and you're interested in that. And then we'll have a follow-up, one more thing on Python here 2 weeks from now, which is basically a Python workshop as it relates to tools that we use in AI. And that's definitely going to be useful for you if you're going to core.
Like NumPy.
Right, exactly. And so with that said, thank you for coming out to this. We actually are going to be hosting office hours, and Calvin has them on Friday nights at 7 o'clock.
So normally, like core, they start next week, but I think it makes sense that since it's happening, you guys had this lecture today. I figured that it may be good for me to have office hours, tomorrow and stuff. So.
Right.
I should have said this, but I'll post on Discord. So, if, for example, if you couldn't make it, or if you have any questions on any of the material, either Python or math, I'll be able to help.
Yeah, office hours are starting next week for core.
Right.
And you guys can come to it too then.
So Calvin's available on Fridays. I'm going to see if I can get a couple other coordinators for that.
Yeah, we have where you have Monday, Tuesday, Thursday, and Friday. We have somebody. I'm still working out my schedule to get another day on there. So.
We typically take feedback too, so if you go to ucfai.org/feedback, it's available.
Places with
I've
feedback.
also put it I put a link on Discord as well, so it really helps us do better with these things. And also too, if you're interested in getting involved in project teams, that is next Monday night. Keep a lookout for that. So if you want to get on with a group of people and work on a project or join some of the ones that are ongoing, definitely come and check that out. I think that's everything.
I wanted to mention a couple of things.
Okay, go ahead.
So I just want to talk about this too. So just some my personal recommendations. So this went really fast. So if you guys want extra practice on it, my suggestion is try taking some of your old C assignments and rewriting them in Python. The other thing you can do is you can go onto some of these websites where they have like challenge problems. So like for example, HackerRank. Try doing some of the easier problems in Python. And I think the other thing you can do is I really highly encourage you as part of the project teams, right, and also a former team leaders, to encourage you guys to look into join our the GBM for the project group formation, because I think it's very helpful when you have people that also want to do the same thing as you. They want to learn Python together. They want to create some they want to do machine learning together and so on. I think that is really, if you have a really good team, which you probably will, it can really be motivational, and it could be probably one of the a really monumental thing in your life. That I think all of the teams, especially my team, they really believed in that. When I asked them what was one of the best things in 2019, one of the things they said was the group, just simply joining the group. So I really highly recommend coming out to that.
Yeah.
Real quick too, just to recommend a couple other resources. So up here, Jordan Du put this lecture together, and just a shout out to him. He's actually the one who had constructed this last section. He recommends learnpython.org. That's where he pulled a lot of this information from. All of that's listed on there, plain and simple, and a lot of what's pulled here is from that as well. You can also check out Automate the Boring Stuff. It's a good series that covers this. It's a book.
Yes.
It's online as a course.
So
in fact, there's a club here.
It's a free book online.
Right. There's also a club here that runs through that exact book and that course as well, Python at UCF. Yeah. So they actually sit down, and all of what we went through, which we tried to blast through in an hour, you can find that stuff there. They break it down and they go through projects on this. Mm-hmm. And I definitely recommend that as well.
And I posted those links. So give yourself the core role, and core announcements. I actually posted some more resources too. And one of them is the link to the book for Automate the Boring Stuff. And there's a free website. But yeah, I mean, there's a lot of resources on Python online. And since most of you had prior programming experience, it's really easy to just repetition to pick up all the syntax. So you'll find yourself never wanting to go back.
But hopefully this was a nice refresher. So again, what we do in core is a lot of working with just these foundations. So
right.
Anyway, thank you so much.
Yeah.